Welcome to Introduction to Geology. I'm Dr. William Patterson. In this module, I'll be discussing the Earth's interior, how we derived the structure of the Earth from seismic waves, and we'll talk a bit about heat flow, how the Earth has cooled over time. Ever since our origin, humans have been scratching around on the Earth's surface, looking for valuable things. Humans have reached a maximum depth of around 10 kilometers, drilling for oil and scientific purposes. Below that, we have to rely on other types of information to determine what lies beneath our feet. We do this by using seismic waves principally. Different types of waves, sound waves, light waves, and seismic waves all have a common characteristic. The speed at which they travel depends on the material through which they're traveling. Light waves travel fastest through a vacuum, more slowly through air, and even more slowly through water. Alternatively, sound waves travel faster through water than through air, and not at all through a vacuum. If you're a scuba diver, you'll notice it's much harder to determine direction of the origin of a sound, because the time at which those sounds reach each of your ears is going to be very close. So your brain isn't able to determine the direction of a sound as it would if you were in the air. Sound waves are basically propagating variations in pressure. Without something to compress, such as water or air, they don't exist. They can't propagate. The more force it takes to compress a material, the faster sound will travel through it. The speed of sound in air, we call Mach 1, is usually about 0.34 kilometers a second, or around 760 miles an hour at the Earth's surface. Now, water is going to resist compression much more than air, so the speed of sound waves in water is going to be correspondingly higher at about 1.5 kilometers a second. Solid materials are even more resistant to compression, such that sound waves travel through them at much higher speeds. For example, sound travels through granite at about 6 kilometers a second, or 13,500 miles an hour, which is pretty fast. There are a couple basic types of waves. As we just mentioned, there are compressional waves, like sound waves, that travel through material with a push-pull motion, while others, known as shear waves, travel with a side-to-side motion, displacing material at right angles to the path of travel. Solids are more resistant to compression than to shearing, so compressional waves travel faster through solids than shear waves do. This phenomena explains why compressional waves are always the first to arrive at a seismographic station, and are therefore called primary waves or P waves. Shear waves, on the other hand, are secondary waves because they arrive second. They're known as S waves. This also explains why the speed of shear waves in gases and liquids is zero, because those materials have no resistance to shearing. Shear waves, therefore, cannot propagate through any fluid, whether it's air, water, or the liquid iron in the Earth's core. It's easy to calculate the speed of an S wave or a P wave by dividing the distance traveled by the travel time. These wave speeds can then be used to infer which materials the waves encounter along their paths. These concepts of travel times and wave paths sound straightforward enough, but complications arise when materials pass through more than one type of material. At the boundary between two different materials, some of the waves bounce off, meaning they're reflected, and others are transmitted into the second material. The waves that cross the boundary between two materials are bent or refracted, as their velocity changes from that in the first material to that in the second material. By studying the speeds at which seismic waves travel and how they're refracted and reflected at Earth's internal boundaries, seismologists have been able to model the layering of the Earth's crust, mantle, and core with significant precision. If the Earth were made of a single material with constant properties from the surface to the center, then P waves and S waves would travel from the focus of an earthquake to a seismograph along straight lines through the Earth's interior, similar to the sun's rays passing through outer space in a straight line. However, when the first global networks of seismographs were installed about 100 years ago, seismologists noticed that seismic ray paths aren't straight lines. The waves are refracted and reflected by Earth's layered structure. At least that was the hypothesis. Based on observations of travel times and the amount of upward refraction of the ray paths, seismologists were able to conclude that P waves travel much faster through rock deep within the Earth than they do through rock at the Earth's surface. That wasn't that surprising. What they did find that surprised them was that after P waves and S waves have traveled beyond about 11,600 kilometers, they suddenly disappear. Seismologists measured distances traveled over the Earth's surface in angular degrees, from 0 degrees at the earthquake focus to 180 degrees at a point on the opposite side of the Earth. Each degree is about 111 kilometers on the surface, so 11,600 kilometers corresponds to an angular distance of 105 degrees, as we see in this figure. When seismologists looked at seismograms recorded beyond 105 degrees from the focus, they did not see the distinct P and S wave arrivals that were so clear on seismographs recorded at shorter distances. Then, beyond about 15,800 kilometers from the focus, or 142 degrees, the P waves suddenly reappear, although they're delayed compared to their expected travel times. S waves, on the other hand, never reappear. In 1906, British seismologist Oldham put these observations together to provide the first evidence that the Earth has a liquid outer core. S waves couldn't travel through the outer core because it's a liquid, and liquids have no resistance to shearing. That was his argument. Thus, there's an S-wave shadow zone beyond 105 degrees from the earthquake focus, where S-wave ray paths encounter the core mantle boundary. Propagation of P waves is a bit more complicated. At about 105 degrees, their ray paths also encounter the core mantle boundary. At that boundary, P wave velocity drops by almost a factor of 2. These waves are refracted downward into the core and emerge at a greater angular distance after the delay caused by their detour through the core. This refraction effect forms a P-wave shadow zone at angular distances between 105 degrees and 142 degrees. When seismologists looked at records of seismic waves made at angular distances of less than 105 degrees from the earthquake focus, they found that waves must have reflected from the core mantle boundary. They label these compressional waves reflected from the top of an outer core as a PCP and shear waves as SCS. The lowercase c indicates a core reflection. In 1914, a German seismologist, Gutenberg, used the travel times of these reflected waves to estimate the depth of the core mantle boundary, which is now put at 2,890 kilometers. This figure also shows the ray paths of some other prominent wave types seen on seismograms, along with the labels seismologists have attached to them. For example, a compressional wave reflected once at Earth's surface is labeled PP, and a shear wave with similar path is labeled SS. Ray paths of these wave types and their internal reflections on seismograms recorded at different angular distances from an earthquake focus. The ray path of a compressional wave through the outer core is labeled with a K from the German word for core. So PKP designates a compressional wave that propagates through the crust and mantle into the outer core and back through the mantle and crust to a seismograph at the Earth's surface. In 1936, Danish seismologist Inge Lehmann discovered the Earth's inner core by observing compressional waves refracted by its outer boundary, which she determined to be at a depth of about 5,150 kilometers. Ray paths through the inner core are labeled with an I, so the waves Lehmann observed are labeled PKIKP. Other seismologists have since observed seismic waves can be used to probe the shallow parts of the Earth's crust. One technique, called seismic profiling, has a number of practical applications. Seismic waves generated by artificial sources, such as dynamite, on land and compressed air explosions at sea, are reflected by geological structures at shallow depths in the crust. Recordings of these reflections has turned out to be one of the most successful methods for finding deeply buried oil and gas reservoirs. This type of seismic exploration is now a multi-billion-dollar industry. Reflected seismic waves are also used to measure the depth of water tables and the thickness of glaciers. On the ocean, compressional waves can be generated by mechanical devices similar to loudspeakers, and oceanographic ships routinely use underwater sound they produce to measure the depth of the ocean and the thickness of the sediment on the seafloor. Fortunately for seismologists, there are thousands and thousands of earthquakes. The travel times of compressional and shear waves from these earthquake events have been used by geologists to develop detailed models of how these wave speeds change with depth in the interior of the Earth. This provides us with the context for developing our models of what is in the Earth, the materials, the physical behavior of that material. Seismologists have measured the velocities of seismic waves passing through various types of materials that make up the Earth, and they can be divided up based on P-wave velocities as felsic rocks, typical of the upper continental crust, we'll use granite as an example here, has a typical P-wave speed of 6 kilometers per second. Mafic rocks, which make up the ocean crust and lower continental crust, which we call gabbros, have a speed of about 7 kilometers a second, slightly faster. Ultramafic rocks, typical of the upper mantle, and this material is called peridotite, has a speed of 8 kilometers a second. These velocities are different because they're dependent upon a rock's density and its resistance to compression and shear, which in turn depends on the chemical composition and crystal structure of the material. In general, higher densities will display higher P-wave velocities. Typical densities for granite are about 2.6 grams per centimeter cubed, gabbro about 2.9 grams per centimeter cubed, and peridotite about 3.3 grams per centimeter cubed. We now know from measurements of P-wave velocities that the upper part of the continental crust is made up predominantly of low-density granitic rocks. Measurements also indicate that no granite exists on the deep seafloor. The crust below the ocean consists entirely of basalt and gabbro overlain by sediment. The velocity of P waves increases abruptly to 8 kilometers a second at the Mohoraichich discontinuity, or MOHO. This marks the base of the crust. That velocity indicates the mantle below the MOHO is predominantly made of peridotite. Seismic data demonstrates the Earth's crust is thin, only about 7 kilometers thick, under the oceans, 33 kilometers under the stable, flat-lying continents, and as much as about 70 kilometers under the high mountains and orogenic belts. The elevations of continents relative to the deep seafloor is best explained by the principle of isostasy that states total weight of lithospheric columns should be the same for continents and oceans. The balance is called isostatic equilibrium. The upper mantle extends from the MOHO to 410 kilometers depth. It's made predominantly of peridotite, a dense ultramafic rock that is in turn composed of pyroxene and olivine. These minerals are relatively silica-poor, enriched in magnesium and iron, more so than those found in typical crustal rocks. S-wave velocities have been used to explore the layering of the mantle. The layering of the upper mantle is caused predominantly by the effects of increasing temperature and pressure on peridotite. Pyroxene and olivine undergo partial melting under the conditions found in the uppermost part of the mantle. At greater depths, increasing pressure forces the atoms of these minerals closer together into more compact, dense crystal structures. The mantle just below the MOHO is relatively cold. Like the crust, it's part of the lithosphere, the rigid layer that forms the plates. On average, the thickness of the lithosphere is about 100 kilometers, but it's highly variable geographically, ranging from almost no thickness near spreading centers, where new oceanic lithosphere is forming from hot and rising mantle material, to over 200 kilometers beneath the cold, stable continental cratons. Near the base of the oceanic lithosphere, S-wave velocities decrease abruptly. This is the beginning of the low velocity zone. At about 100 kilometers depth, the temperature approaches the melting temperature of peridotite, partially melting some of its minerals. Although the component that melts is small in most places, less than 1%, it's sufficient enough to decrease the rigidity of the rock, which slows the S-waves passing through it. Because partial melting of the rock allows it to flow more easily, geologists identify this low velocity zone with the top part of the asthenosphere, the weak ductile layer on which the rigid lithospheric plates slide. The base of the low velocity zone can be found at about 200 to 250 kilometers below the oceanic crust, where S-wave velocities increase to a value consistent with solid peridotite. The low velocity zone is not as well defined under stable continental cratons, where cold lithospheric mantle extends to these depths. At depths of about 200 to 400 kilometers, the S-wave velocity again increases. Within this zone, pressure continues to increase with depth, but the temperature does not rise as rapidly as it does near the surface due to the effects of convection within the asthenosphere. Combined, the effects of pressure and temperature decrease the amount of melting with depth and cause the rock rigidity, and thus S-wave velocity, to increase. At about 400 kilometers below the surface, S-wave velocities increase by about 10% within a narrow zone of less than 20 kilometers. This jump in S-wave velocity is explained best by a phase change in olivine, the major mineral constituent of the upper mantle. When olivine is squeezed with high pressure in the laboratory, the atoms that form its crystal structure collapse into a more compact arrangement at the temperatures and pressures that we would find at 410 kilometers depth. The increases in the P and S-wave velocities measured for this phase change in the laboratory match the increase observed from seismic waves passing through this depth. At a depth of about 660 kilometers, the S-wave velocity abruptly increases again, indicating another major phase change in olivine to an even more closely packed crystalline structure. Because it contains at least two major phase changes, the layer between 410 and 670 kilometers depth is called the transition zone. Phase changes are transitions in a rock's mineralogy, but not in its chemical composition. Some geologists have suggested that the increase in wave velocities at 660 kilometers is due in part to a change in chemical composition of mantle rock. This argument is critical to understanding the plate tectonic system because a chemical change would imply that the convection that drives plate tectonics does not penetrate much beyond this depth. In other words, that convection in the mantle is stratified. Evidence from detailed studies of mantle structure now indicate very little, if any, chemical change in this region of the mantle. Below the transition zone at 660 kilometers, seismic wave velocities increase gradually and do not show any more unusual features until we get close to the core mantle boundary. This relatively homogeneous region, with a thickness of 2,000 kilometers, is known as the lower mantle. The lower mantle is convecting and exchanges mass with the upper mantle, driven in part by slabs of oceanic lithosphere subducting through the upper mantle into the lower mantle. At the core mantle boundary, about 2,890 kilometers below the surface, we encounter the most extreme change in properties found anywhere in the Earth's interior. Based on the behavior of seismic waves reflected by this boundary, seismologists can tell that this is a very distinct interface. Material changes abruptly from solid silicate rock to a liquid iron alloy. Because of the complete loss of rigidity, the S-wave velocity drops from about 7.5 kilometers a second to 0. P-wave velocities decrease from 13 kilometers a second to about 8 kilometers a second, resulting in the core shadow zones. Alternatively, density increases by about 4 grams per centimeter cubed. This density difference is greater than the increase in density from the atmosphere to the lithosphere at the Earth's solid surface. This density difference keeps the core mantle boundary very flat, preventing any large-scale mixing of the mantle and core. The core mantle boundary appears to be very active. Heat conducted out of the core increases the temperature at the base of the mantle by as much as 1,000 degrees centigrade. In fact, the paths of seismic waves that pass near the base of the mantle show strange complications, suggesting a region of exceptional geological activity. In the thin layer above the core mantle boundary, there's a steep decrease in seismic wave velocities of about 10% that may be an indication the mantle in contact with the core is partially molten, at least in some places. Some geologists believe that this hot region is the source of mantle plumes that rise to the surface, creating hotspots such as Hawaii and Yellowstone. The lowest boundary layer in the mantle, a region about 300 kilometers thick, could be the graveyard of some subducted lithospheric material, such as the dense iron-rich parts of the oceanic crust. It's possible that this zone experiences an upside-down version of the tectonics we see at the Earth's surface, with accumulations of heavy iron-rich material forming chemically distinct anticontinents that are continually pushed across the core mantle boundary by convection currents. This brings us to the core. Many lines of evidence support the hypothesis that Earth's core is made of iron and nickel. These metals are abundant in the universe. In addition, they're dense enough to explain the mass of the core, about 1/3 of the Earth's total mass, and they're consistent with the theory that the core formed by gravitational differentiation, the iron catastrophe. This idea of an iron core was first proposed in the late 19th century, reinforced by discoveries of meteorites made almost entirely of iron and nickel, which presumably came from the breakup of a planetary body that also had an iron-nickel core. Laboratory experiments at appropriately high pressures and temperatures have led to a revision in this hypothesis. A pure iron-nickel alloy is about 10% too dense to match data for the outer core. Therefore, it's been hypothesized that the core includes minor amounts of some lighter elements. Oxygen and sulfur are leading candidates, although the precise composition remains a subject of debate. Seismology tells us that the core below the mantle is liquid, but the core is not liquid to the very center of the Earth. As Lehman first discovered, P waves that penetrate depths of 5150 suddenly speed up, indicating the presence of an inner core, a metallic sphere about 2/3 the size of the moon. Seismologists have demonstrated that the inner core transmits shear waves, confirming early speculations that it is solid. In fact, some calculations suggest the inner core spins at a slightly faster rate than the mantle, acting like a planet within a planet. Evidence for a hot internal Earth can be seen everywhere. Volcanoes, hot springs, high temperatures measured in boreholes and mines all point to the Earth being hotter as we go deeper. The Earth's internal heat is generated by several sources. During the planet's origin, kinetic energy was released when planetesimals bashed into each other. Gravity then released energy during differentiation, with the core getting heated up as heavier elements sank towards it. And to this day, the decay of radioactive isotopes in the Earth's interior generates new heat. Once the Earth formed, it began to cool off, and this cooling led to ultimately a crust forming on the surface. However, heat has continued to flow from the interior of the Earth to the surface over the last 4.56 billion years. The Earth is cooling off through two primary mechanisms: the transport of heat by conduction, and through the more efficient transport of heat via convection, or overturning. Conduction is going to be the dominant force in the lithosphere, whereas convection is much more important throughout most of the Earth's interior. Heat energy is simply the vibration of atoms. Higher temperatures mean more intense vibrations. The conduction of heat occurs when thermally agitated atoms and molecules move past one another, mechanically transferring kinetic energy from a hot place to a cold place. Heat is transferred from regions of high temperature to regions of low temperature via this process. Materials such as minerals vary in their ability to conduct this heat. Metal, for instance, is a much better conductor than things like plastic or even rocks. Rock and soil turn out to be very poor conductors, which is why underground pipes are less susceptible to freezing than those above the ground. Rock conducts heat so poorly that a lava flow 100 meters thick takes about 300 years to cool from 1,000 degrees to 20 degrees. Moreover, the cooling time of a layer increases with the square of its thickness, such that a lava flow twice as thick, 200 meters, would take 4 times as long to cool, or about 1,200 years. The conduction of heat from the outer surface of the lithosphere causes the lithosphere to cool slowly over time. As it cools, thickness of the lithosphere increases. Rock contracts and becomes denser when it decreases in temperature, such that the average density of the lithosphere must increase over time. According to the principle of isostasy, its surface must sink to lower levels to compensate for this. This is why mid-ocean ridges stand higher than the surrounding crust, because the lithosphere there is young, hot, and thin, whereas the abyssal plains are deep because the lithosphere there is old, cold, dense, and thick. From these ideas, geologists have constructed a simple but precise theory of seafloor topography that uses conductive cooling to explain the large-scale features of ocean basins. This theory predicts that ocean depth should depend primarily on the age of the seafloor. This means that seafloor that is 40 million years old should have subsided twice as much as seafloor that is only 10 million years old. This simple mathematical relationship matches seafloor topography near mid-ocean ridges spectacularly well. Conductive cooling of the lithosphere accounts for a wide variety of other geological phenomena, including the subsidence of passive continental margins and thermal subsidence basins. It characterizes why the amount of heat flowing out of the oceanic lithosphere is high near the spreading centers, decreasing as the oceanic lithosphere gets older. And it tells us why the average thickness of the oceanic lithosphere is about 100 kilometers. The development of this theory is one of the great successes of plate tectonics. Conductive cooling does not explain all aspects of heat flow through the Earth's surface, however. Marine geologists have found that seafloor older than about 100 million years does not continue to subside as this theory would predict. Additionally, simple conductive cooling is far too inefficient to account for the cooling of the Earth over its entire history. It can be shown that if the 4.5 billion-year-old Earth cooled by conduction alone, very little of the heat from depths greater than about 500 kilometers would have reached the surface. The mantle, which was molten in Earth's early history, would be far hotter than it is now. To make sense of these observations, we have to consider the second mode of heat transport, convection, which is much more efficient than conduction in getting heat out of the Earth's interior. When a fluid, either a gas or a liquid, is heated, it expands and rises because it has become less dense than the surrounding material. This upward movement of the heated fluid displaces cooler fluid downward. There, it's heated and then rises to continue the cycle. This process, called convection, transfers heat more effectively and efficiently than conduction because the heated material moves, carrying its heat with it. Convection is the same process by which water is boiled in a coffee maker. Liquids conduct heat poorly, so a kettle of water would take a long time to boil if convection did not distribute the heat rapidly. Convection is what moves heat. Convective movement in the outer core distributes heat through the core very effectively, and it generates the Earth's magnetic field. At the core mantle boundary, heat from the core flows into the mantle. The existence of convection in the solid mantle is surprising. We now know that the mantle rock below the lithosphere behaves as a ductile material. Over long periods, it can flow like a viscous fluid. Seafloor spreading and plate movements are direct evidence of this solid-state convection at work. Hot mantle material rises under mid-ocean ridges, builds new lithosphere, which cools as it spreads away. In time, it sinks back into the mantle at subduction zones, where it is eventually resorbed and reheated. It's this process that carries heat from the Earth's interior to its surface.
You gotta keep the devil down in the hole. He's got the fire and the fury and